Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we discussed the nonlinear V-blast receiver for MIMO communication systems. We also said that this receiver is based on the SIC principle, that is successive interference cancellation, where symbols are estimated and their impact is successively cancelled followed by detection of other symbols and so on. This is an iterative procedure essentially, and we had also seen that in this procedure you consider the matrix Q, which is the pseudo inverse, the left inverse of the matrix H. However, you do not employ zero forcing, you only cancel one stream employing the row in corresponding row in Q, and then you remove its impact and followed by the detection of other schemes. Okay. And we had also seen that the advantage of this scheme, the significant advantage of this scheme is that the diversity order of the successively decoded frames is higher. That is, as you keep decoding frame symbols, the diversity order progressively increases for the later decoded symbols in this procedure, thus enhancing reliability. Okay. And we had also seen an example of a V-blast system, of a simple V-blast receiver for a 2x2 MIMO system. Then we had also talked about beam forming, that is forming a beam in a MIMO communication system, that is instead of employing all the modes, we transmit only in a certain given direction in n dimensional space, which is known as beam forming. For this purpose, we said that the x bar vector can be formed as a beam in the direction of V1 bar, where V1 is the dominant right singular vector of the matrix H, employing a single transmitted symbol x1 tilde, and corresponding to that we said the received SNR was sigma 1 squared p over sigma n squared. So, the gain of this channel is sigma 1 squared, which extracts the dominant or which corresponds to the dominant singular mode of this MIMO channel. And further we said that this scheme is maximal ratio transmission, it is termed as MRT, which essentially extracts corresponds to the yields the channel gain corresponding to the largest singular value or the larger or the strongest mode in the MIMO channel. All right. And at that point, and with that essentially that concludes our discussion of the MIMO module. So, let us start with summarizing. Let me start by summarizing the MIMO model, and then I will continue with the next module in this course on 3G, 4G wireless communication systems. So, let me summarize MIMO module. In this MIMO module we had start with, so in the MIMO module we had started with first the MIMO architecture, we started with the MIMO architecture and system model. We started with the MIMO architecture with its multiple antennas at the transmitter, multiple antennas at the receiver. We started with the schematic, we developed a system model in terms of y equals hx plus n, where x is now a vector, y is now a vector, and h is a matrix channel. We also looked at MIMO receivers. We first started with linear MIMO receivers. We said, for instance, one linear MIMO receiver is the MIMO zero forcing receiver. Simply abbreviated as MIMO ZF, that is the MIMO zero forcing receiver. It employs the left inverse of H or the pseudo inverse of H when the number of rows of H or the number of receive antennas is essentially greater than or equal to the number of transmit antennas. And we also said that one disadvantage of the MIMO zero forcing is that it results in noise enhancement. Hence, we also proposed another MIMO receiver architecture, that is the MIMO MMSE receiver. So, we also propose the In fact, this is the Mimo LMMSE receiver. I will simply call this the Mimo MMSE receiver, where MMSE stands for minimum mean So, essentially this Mimo MMSE receiver, it minimizes the mean square of error of detection at the receiver, and we also saw that it has superior properties in the sense that it does not result in noise enhancement because of its unique structure. Then we focused on something important, which is the singular value decomposition of the we focused on the singular value decomposition of the Mimo channel. This is also termed as SVD. So, we focused on the singular value decomposition of the Mimo channel. This is termed as the SVD. We also said this is based on a pre-coding and receive beam forming at the receiver. This is based on a pre-coding structure essentially. This is also essentially a transmit pre-processing that has to be done at the Mimo transmitter before transmission. But the big advantage of this is, as we saw, it results in parallelization of the Mimo channel. This SVD results in parallelization of the Mimo channel, or in other words, decoupling of the different spatial modes of the Mimo channel. So, it presents a convenient framework. So, it results in or decoupling of the spatial modes of the Mimo channel. That is a big advantage, because now there is no interference from the co-streams at the receive antenna. Once you post process using U Hermitian, what you have is it appears as if this Mimo channel consists of T independent channels, X1 transmit across channel 1, X2 transmit across channel 2, and so on. So, we had looked at this, how the Mimo channel can be decoupled by transmit pre-processing and some post-processing, so as to decouple the channels and essentially make them interference free from the other symbols. Okay. And in this context, we are also seen the SVD based optimal power allocation. We are also seen SVD the SVD based optimal power allocation for capacity maximization, optimal power allocation for in fact, we also said that this is derived as the water filling based power allocation solution. This we derived a water filling we also derived a water filling based power allocation solution. And then we looked at an interesting framework to characterize the asymptotic Mimo capacity. We characterize the asymptotic Mimo capacity, all right. And further, we also said that the Mimo capacity linearly increases as the minimum of R, T for the same transmit power, and that is in fact what results in the high throughput of these MIMO wireless communication systems. Then we also looked at the unique framework of orthogonal space time. We also looked at orthogonal space time block code or OSTBC. So, we looked at orthogonal space time block codes or OSTBC. In this context, we had looked at in detail at the Alamuti space time block code, the Alamuti OSTBC, which is essentially intended to 1x2 MIMO system. And we also saw an example of a rate half. We said Alamuti is in fact full rate or R equals 1 OSTBC, and we also saw an example of a rate half, another OSTBC for 1x3 MIMO systems, which essentially means one transmit antenna, one receive antenna and 3 transmit. It essentially has one receive antenna and 3 transmit antennas, and we said this is a rate half code. This is not a full rate code, but this is a rate half code, and in fact this is a rate half orthogonal space time block code. All right. And then finally, we had seen a nonlinear receiver, V blast, which is vertical blast, which stands for vertical Bell Labs layered space time architecture. Right. So, this is a nonlinear receiver. In fact, as we had also summarized today, is based on successive interference cancellation. And finally, we had looked at beam forming in MIMO systems. We had also looked at and this is based on the principle of maximum ratio transmission. We had introduced the concept of MRT, which stands for maximum So, we had introduced the principle of MRT, which stands for maximum ratio transmission. All right, we had introduced. So, the last topic we talked about was beam forming in MIMO system. So, with that we come to the conclusion of the MIMO module. This is a summary of the different topics that we had covered in this module. So, please again go over these to enhance your understanding of each of these concepts. And now I will move on to the next module in the course, which is fairly important and which has come to attract a lot of attention. This is OFDM. I will explain what OFDM stands for. So, the new module that we are going to start talking about is OFDM, which stands for orthogonal frequency division So, OFDM basically stands for orthogonal frequency division multiplexing. All right, and this is a revolutionary communication technology. And why is this a revolutionary communication technology? OFDM essentially forms the basis for all 4G wireless communication systems. For instance, if you remember, what we had talked about earlier in one of the very first lectures of the course. We looked at 3G technologies. We said CDMA forms the basis for 3G technologies. However, all 4G technologies are based on OFDM. So, OFDM is very important because OFDM forms the basis for futuristic 4G or fourth generation 4G, which is essentially fourth generation wireless communication systems. Alright, so OFDM or orthogonal frequency division multiplexing is a very important technology. In fact, it is a revolutionary, radical technology in wireless communication systems, because it is a key technology for 4G wireless communication systems. For instance, let me briefly summarize what kind of 4G wireless communication systems we looked at. We looked at the next generation cellular networks based on LTE. This is the 4G cellular expected to be the dominant 4G cellular standard, which stands for long term this is LTE, which also stands for long term evolution. All right. So, this is basis for OFDM, and this is based on OFDM. LTE is based on OFDM, and in fact, OFDM is also the basis for the competing cellular standard of WiMAX. This is also another 4G cellular standards. In fact, 4G cellular and also 4G cellular standard, and this stands for worldwide interoperability for microwave access. In fact, WiMAX also has capabilities for fixed wireless access, nomadic wireless access, and other modes of wireless, not just simply cellular, but also fixed broadband wireless access, essentially for last mile wireless access, reaching from the tower to the home and so on, or the hub to the home and so on. All right. So, OFDM is the basis for these two key next generation wireless communication technology, and the reason is because OFDM is a broadband wireless technology and has several advantages. In fact, it supports data rates which are in excess of 100 Mbps. If you look at LTE and WiMAX, for instance, LTE claims that it can support data rates in excess of 100 Mbps. So, OFDM is a key broadband wireless technology which supports data rates in excess of. So, OFDM is a key broadband wireless technology, and it supports essentially, it is one of the key technologies which supports data rates in excess of 100 Mbps, which is crucial in next generation broadband wireless communication systems and communication networks. All right. And also further, not only cellular standards, but OFDM is also the basis for LAN standards. So, if you looked at 802.11a B, not B, I am sorry, 802.11a, G and N standards, these are also based on OFDM. in fact A2.11n can progressively support data rates up to around 200 Mbps. So, 8.11n can support data rates around 200 Mbps and more. So, OFDM is also a basis for these wireless LAN standards. These are the, as we all know, the 8.11 suite of standards, which is the IEEE suite of standards, is essentially the dominating set of wireless LAN standards. All right, and as we said, so these are based on some very interesting and convenient properties of OFDM, which we are going to start looking at in this module. Okay. So, in OFDM, for instance, even before going to OFDM, let us try to understand what is the scenario for communications that existed previously to OFDM. So, we consider a bandwidth. So, let us start by considering a bandwidth of B available for communication. So, consider a bandwidth B available for when I say a bandwidth B, I am considering the two-sided bandwidth. Here I am considering the two-sided bandwidth B that is available in a traditional communication system. Typically, when bandwidth B is available for communication, for instance, when I look at this two-sided bandwidth B that is available for communication, typically we employ a symbol time T. This is the symbol time, which is equal to 1 over B. So, I employ a symbol time T, which is equal to 1 over B, and I send symbols every T. So, I send one symbol every T. Technically, if you have a bandwidth of B, you can send two symbols on different the cosine and sine carrier, but for the sake of simplicity, I am just simplifying it to saying we are using one of the orthogonal carriers, and I am sending symbols every T seconds. So, let me summarize that idea. Bandwidth B transmit one symbol every T seconds, where T is in fact 1 over B. So, every T equals 1 over B, you transmit every T equals 1 over B, you transmit a symbols, and in fact the symbol rate equals 1 symbol every 1 over B seconds, which is nothing but B, and that is what is. So, if you have a bandwidth of, for instance, let us say 100 megahertz, you can roughly transmit symbols at 100 megabits per second. Right? That is the essential idea in a communication system, that is where T equals 1 over B, which is 1 over 100 megahertz, which is 10 to the power of minus 2 microseconds, you transmit one symbols, that is at T equals 1 over 100 megahertz. So, every 10 to the power of minus 2 microseconds you transmit one symbol, which essentially gives you a symbol rate of 100 megabits per second. All right, and this is traditionally what you do is you have this baseband, you modulate symbols on the baseband, employ a single carrier to modulate this stream and transmit it in the allocated passband bandwidth. All right. So, this is the philosophy, or this is the conventional communication system which is known as single carrier communication. This is a single carrier communication system. this is a single carrier communication system. As we have seen, this is a single carrier communication system. What it means is there is one carrier, this is a which means there is a unique carrier, that is one carrier, and that consumes the entire bandwidth, that occupies the entire communication bandwidth there is a single communication carrier and that occupies the entire communication bandwidth of B. That is the philosophy of a conventional single carrier system, all right. And if you look at the transmission itself, the transmission can roughly be expressed as follows, as St equals xk for kt less than equal to t less than equal to k plus 1 t, all right. For instance, between if k equals 0, between 0 and t you transmit x0. So, x0 between 0 less than equal to t less than equal to t, you transmit x1 between t less than equal to t less than equal to k plus 2t, which is 2t, you transmit x2 in 2t less than equal to t less than equal to k plus 1, which is 3t, and so on. So, your symbols essentially you have a slots of duration capital T, which is 1 over b, that is, as we said before, one symbol every you are transmitting one symbol every t seconds. Okay. So, you are transmitting one symbol every capital T seconds, but t itself this is equal to 1 over b. Okay. So, that is what we said is essentially the principle of a single carrier system, and the rate is obviously 1 over b, which is b symbols per second. Okay. Now, as against this, let us consider something different. I will not explain why we need to consider something different. I will not explain the motivation at this point, but let us start by considering it, and I will explain the motivation once we go a little bit further into this thing. All right. So, let me start by explaining the motivation. Let me consider a system in which I have a bandwidth of b. Again, remember I am talking about the two-sided bandwidth, and what I am going to do is, instead of having one single carrier, I am going to divide it into multiple carriers. Divided into multiple carriers at a spacing of b over n. So, I have a bandwidth of two-sided bandwidth b. I am going to divide this into multiple carriers at spacing b over n. That is what I am going to do. I am going to divide it into multiple sub carriers. Precisely how many carriers are there? There are n carriers. In fact, these carriers occupy smaller bands. So, these are known as sub carriers. So, I am dividing the available bandwidth b into n sub carriers. In fact, let me finish drawing this diagram. This is minus b by n, this is minus n by 2 minus 1 b by, and in fact, so if you look at this, this is the sub carrier spacing is obviously b over n. I am using n sub carriers. So, these are all these together are n subcarriers. Why subcarriers? Because I am dividing the bandwidth into smaller bands and in smaller sub bands, and in each of them I am using a carrier. Each carrier represents this smaller sub band, hence it is a subcarrier. In fact, this is a sub band. This is a sub band of the. So, I am decomposing into multiple sub bands. I am using subcarriers in each of these bands, and the net bandwidth is allocated to me. Okay. So, I am dividing it into n subcarriers, and the spacing is b by n. This is in fact the subcarrier this is in fact a multi-carrier system. So, this is an example of a multi-carrier system. In fact, in this system each carrier, each of the n subcarriers has a much smaller bandwidth compared to the bandwidth of a single carrier system. All right. So, this is a what we have here is a multi-carrier or a multiple carrier system. Okay. Now, for instance, let me give you an example. Let me consider a bandwidth b. Consider b which is equal to 256 kilohertz. Typically n, the number of subcarriers, typically n either equals values such as 256, 5112, 1024. Typically the number of subcarriers is a power of 2. Typically n, which is the number of subcarriers, is a power of 2. All right. So, typically the number of subcarriers is a power of 2. We will see the reason for this soon. Let us see, since it is typically a power of 2, why it is a power of 2, we are going to see it shortly in this lecture or the subsequent lecture. For instance, let us say a bandwidth of 256 kilohertz. Let me consider n equals, let us say 64 subcarriers, then the bandwidth per subcarrier is b over n, which is equal to 256 hertz divided by 256 kilohertz divided by 64 equals 4 kilohertz. So, in this example where I am employing a total bandwidth of 256 kilohertz, I am dividing it into 64 smaller sub bands, and each of those sub bands has a bandwidth of 256 divided by 64, which is equal to 4 kilohertz. All right. So, each of those has sub bands has a bandwidth of 4 kilohertz, and that is what we are saying here essentially. Now, fine, I have divided into several sub bands of much smaller bandwidth. How am I going to transmit? How am I going to transmit information symbols on these subcarriers? So, we have to consider the multi-carrier transmission scheme. So, let us consider the multi-carrier transmission scheme. Okay. So, this multi-carrier, in this multi-carrier transmission, I have seen the ith subcarrier is given as I times b over n, that has a center frequency I times b over n. This is the center frequency of of the ith subcarrier, where this index I is such that minus n by 2 or minus of n by 2 minus 1 is less than or equal to I is less than or equal to n by 2. All right. So, we are transmitting the ith subcarrier. In fact, I am going to denote this by f of I. So, f of I, which is the ith subcarrier, has a bandwidth of b over n, and it is centered at I times b over n, where the index I has this range as given below. Hence, let me consider xi, which is the data that is transmitted on this ith subcarrier. So, denoting by xi the data xi is the data that is transmitted on the ith subcarrier. In fact, previously remember we had only one carrier. So, we are transmitting only one data stream. Now, I have n subcarriers. So, I can transmit n data stream. So, I am denoting by I the essentially the ith data stream. This is the data that is transmitted on the ith subcarrier. In fact, the modulated signal on this subcarrier is given as SIT equals xi e to the power of j 2 pi FIT. This is the modulated data stream. Okay. So, this as we see is the data that is transmitted on the ith subcarrier. So, this is the data that is transmitted on the ith subcarrier, and this Fi, this is the center frequency of the ith subcarrier, which is I times b over n. All right, Fi is essentially I times b over n. This is the center frequency of the ith subcarrier, and in fact, I have n such subcarriers. So, I have n such data streams. All right. In fact, I am going to write this as xi times e power j 2 pi I b by n over t. All right, because remember the center frequency of this subcarrier is I times b over n t. Okay. Okay. So, and as we said again, let me reiterate again, now there are n subcarriers, hence there are n data streams. So, there are now n subcarriers, hence we have n data streams, hence there are n subcarriers, hence there are n data streams. These are indexed by x of I. Basically, xi denotes, this denotes the ith or essentially the ith set of symbols which can be modulated onto these subcarriers. All right. So, that is what we have seen. So, now how does multi-carrier modulation work? I mean, how do we transmit the signal? We simply sum up these signals corresponding to these n data streams, in fact, the modulated n capital N data streams, and transmit them together. So, multi-carrier transmission. So, let us look at so we have Si of t, which is the ith transmitted stream. So, what I am going to do is I am going to form a composite transmit signal St equals summation over I of Si of t. So, what I am going to do, this is essentially the composite signal this is the composite transmit signal comprising of the n different transmit streams which have been modulated onto the n different subcarriers. In fact, you can see this is modulated onto the ith stream, ith data stream, modulated onto the ith this is the ith data stream that is modulated onto the ith subcarrier. In fact, I can represent this as St equal to summation of I summation over I Si of t, which is nothing but, if I expand this out, this is xi e to the power of j 2 pi fi of t, where this is xi is the data, that is the ith data stream, and fi is the subcarrier corresponding to the ith subband, and this is equal to summation over I xi e to the power of j 2 pi I b over n. All right. So, this is the composite transmitted multi-carrier signal. Remember, we are still not talking about OFDM, we are still talking about multi-carrier transmission only. All right. So, one should not confuse this with OFDM. OFDM will be introduced subsequently. All right. So, this is the multi-carrier composite this is the multi-carrier composite transmitted signal. All right. Now, this is the transmission scheme. So, we illustrated a transmission scheme. Now, this is of course only complete if we illustrate a corresponding detection scheme, because fine, we can sum all these data signals and all these information streams and transmit them over subcarriers, but this is only going to be complete if we introduce a compatible or some symbols, some scheme for detection of these composite signal at the receiver. All right, only then can I claim this, use this transmission scheme meaningfully. So, let us talk about the data detection, the corresponding data detection at receiver. So, the multi-carrier So, let us talk about multi-carrier data detection. Let me now for the moment ignore noise. I am not going to consider noise, just to illustrate the detection scheme. So, I am going to consider a received signal yt, which is in fact equal to the transmitted signal st equal to summation xi e to the power of j 2 pi fi of t. All right. So, this is the received signal s of t. Of course, this is valid in the absence of noise. This is valid in the absence of noise. and remember I am only assuming this at this point to simplify the illustration, all right. Even with the noise present, this scheme is valid, all right. So, let me just for the moment to illustrate this, to assume a simplistic model for illustration, I am assuming the absence of noise. Now, what I am going to do is I am going to coherently demodulate each stream with the corresponding subcarrier. So, what the receiver, the detection scheme is coherent demodulate each stream with So, what I am going to do? I am going to coherently demodulate each stream, that is I am going to take this composite signal that is received, and I am for each stream, to recover each stream I am going to coherently demodulate it with the corresponding subcarrier. What I mean by this is, for instance, let me take this composite signal y t, which is the composite received signal. I am going to correlate it with e power j 2 pi f L of t conjugate, that is this is nothing but the lth subcarrier, and I am coherently I am multiplying with the conjugate, which is in fact I am doing a match filtering kind of operation. This is nothing but a correlation. So, this is also nothing but a correlation. I am going to integrate from 0 to the duration is n over b, and I have a scaling factor which is b over n. I am going to motivate why this integral is of duration 0 to n over b slightly later, but essentially what I am doing here is I am doing a matched filtering sort of operation, where I am correlating the composite signal with the coherent subcarrier. Here in this case I am correlating it with the lth coherent subcarrier. Okay. So, this I am going to represent this as y t. Remember, now I am going to substitute the expression for y t as x I, as summation over I x I e to the power of j 2 pi I b by n over t. I am taking this whole signal, which is the composite signal. I am multiplying this by e to the power of minus j 2 pi. In fact, f of L I will replace it as L times I am going to replace f of L as L times b over n t. All right. I am going to take I am taking this composite signal, I am correlating with the lth coherent subcarrier, integrating it over 0 to n by b, and this b by n is a simple scaling factor. Okay. Now, let us see what happens in this scenario. This can simply be represented as, I will take the summation out of the integral now, and this can simply be represented as b over n summation I integral 0 to n over b summa x I e to the power of j 2 pi I minus L b over n t dt. All right. So, now look at this, this is b over n summation I 0 to n over b x I e to the power j 2 pi I minus L b over n t. Let me call this as some k. Okay, let me call this as some k. In fact, this is equal to b over n summation I 0 to n over b, or now that because I am calling that by k, it becomes x k e power, or let me just let this remain as I j 2 pi k f naught of t dt, where f naught is now the fundamental frequency. Look at this, f naught is being defined as b over n, which is the fundamental frequency. If you are familiar with Fourier series, you know that, and you can see here that all the other frequencies are in fact the multiples, they are all some I minus L f naught, which are essentially the multiples of these fundamental frequency. So, if I integrate over 1 over the period, if I integrate over 1 over f naught, so the period t naught equals 1 over f naught equals n over b, all right. This is the fundamental period, this is nothing but the fundamental period of this system. This is the and you can see here in this scenario, when I integrate this from 0 to n over b, all these terms go to 0 except when k equals 0, which corresponds to I equals L. So, this integral, so let me again simplify this, this integral e power j 2 pi I minus L b over n t from 0 to b over n, which is n, or I can write it from 0 to n over b. This integral equals 0 if I not equals L, and this integral equals, in fact, if you look at this, if I equals L, this integral becomes 0 to n over b e power j 2 pi I minus L, I equals L, hence this is 0, e power j 2 e power 0 is 1, hence this integral becomes 0 1 dt equals n over b equals. So, this integral equals n over b if I equals L. Hence, what we are saying is, when I coherently demodulate with the nth subcarrier, all the other subcarriers are orthogonal to this subcarrier. That is why coherent demodulation results in an output of 0, while only the nth subcarrier survives. So, this is an important idea. In fact, what we are seeing here is essentially, let me summarize this here. All subcarriers except nth, all subcarriers except nth subcarrier, all subcarriers except nth subcarrier are essentially, they result in an output of 0, they are orthogonal. Hence, I can essentially coherently demodulate by correlating with e power j 2 pi f L of t, that is essentially I am multiplying by e power minus j 2 pi f L of t and integrating over the fundamental period, which is 0 to n over b. And now, what we have is obvious, we can write from here. Let us go back to see what we had earlier. What we had here is, I can write this b by n summation of I am going to write this as what we have after demodulation is, after demodulation with the coherent nth after demodulation with lth coherent subcarrier, what I have is, I have this is equal to B over n into XL into the integral n over B plus rest all subcarriers give 0, hence this results in XL. So, I can employ coherent demodulation at the receiver and coherently demodulate with corresponding subcarrier for each subcarrier to receive each symbol. So, I do this with n different subcarriers, I demodulate with n different subcarriers and I can recover the n different symbols. This is the principle of multi-carrier transmission, all right. Multi-carrier modulation, multi-carrier transmission and multi-carrier detection or reception. Okay. So, at this point, due to shortage of time, I will end this lecture at this point and we will continue with this idea in the next lecture. Thank you.